So today we're going to take a look at section 2.1. It's titled Measures of Change Over an Interval. In particular, we're going to look at 3 different types of change. At least 2 of them you've done before in an algebra type class. So the first one is actually just called change. Change actually takes 2 y values and subtracts them. So f of b minus f of a. And one of the ways that you can think about this is that it's the newer y value minus the older y value. So usually something that happened, today compared to something that happened 3 weeks ago or 2 months ago or something like that. Percent change is the one that's most likely to be new to you. This is calculated much the same way in the sense that you still have f of b minus f of a. But what it does is it divides by f of a and multiplies by 100%. If you want to use this idea of new minus old, you can actually think about it as new minus old divided by old times 100. What this does is it gives you some kind of a comparison. How much has something changed compared to how much was it originally? So if you actually go and you look at KFOR is the news source that I have used all of my data from when I've been collecting data for COVID for Oklahoma. And every single day they will tell you the percent change in cases from the day before. So they take today's number of cases, total, like the cumulative number, minus yesterday's number of cases. They divide by what it was yesterday and they multiply by 100. I've even checked them a few times just to make sure that they weren't screwing up their math. So yeah, that's percent change. It's a comparison. How does today's cumulative compare to yesterday's cumulative? That's what actually that's calculating. Average rate of change is one you've seen before. F of b minus f of a, that's an a, over b minus a. What is that? Martin? It's slope. This is just slope. It's y2 minus y1 over x2 minus x1. It's just another way of expressing slope. Yeah, good observation. Okay, so these are the calculations we're going to be looking at of change. We're also going to talk about how we describe something having changed, the description pieces that we will identify. Hang on just a second, sorry. Make sure everybody's got it down. Okay, so there's 4 different things that we will use when we're describing change. So it's going to feel kind of like, who, what, when, where, why, and how, kind of like that. Not got quite that much. But it's going to be when. Specify the interval. It was from 3 weeks ago till today, right? It was over the last 6 months. It was over the last 5 years. It was from 2010 to 2012. Specify the interval. What? What's changing? The number of COVID cases. The percentage of students at OBU who are from Oklahoma. The number of days it takes before the strawberries ripen on the vine. Right? What's changing? How? How just indicates did it increase or did it decrease? And it's in a past tense because it's always over an interval of time. So it increased by something or it decreased by something. It's pretty easy. Usually it has to do with the sign. Did you get a positive sign or a negative sign? If you got a positive sign, it increased. If you got a negative sign, it decreased. And then the by how much indicates the amount that it increased or decreased. So it's a numerical value with units. Right? Cases per week, cases per day, percentage of students per year. Okay? Those kinds of things. How did it change over the time period? By what amount? All right, so we're going to take an example where we calculate all of the different types of change, which is change, percent change, and average rate of change. And then we're going to write a sentence interpreting each. Now, anytime your directions say in a sentence interpreting each, the sentences are almost identical. They're just going to change the by how much at the end, because that's where your actual calculation comes into play. So it's not like it's really three separate sentences. It's really like it's the same sentence three times with a tiny little change, okay? All right, so the first thing we're going to do is to calculate each of the values. So we'll do change first. And our information says the following. The number of internet users in China in 1997 was 0.9 million. And in 2000 was 12 million. All right, so what two values would I be subtracting if I'm looking for how that changed?
12 minus 0.9.
Yeah, it's the newer or later value minus the earlier one, 12 minus 0.9. And what would that give me? Should be 11.1, right? 11.1. 11.1 what? There's always units. Always units on what we just calculated. Million what? Yeah. Million internet users. Okay, does that make sense? The cool thing is that once you've calculated change, you've got the numerator for both of the other two equations, or two formulas that we're going to find. So that's change. Percent change is the same numerator, so it's 12 minus the 0.9, or you could write 11.1 if you want. Kind of like writing it as a 12 minus 0.9 because you can see the 0.9's matching up as I'm dividing by it, because it's always the second value that matches with the denominator, or the earlier or the old value that matches with the denominator. And then it's times 100%. So we need 11.1 divided by 0.9 and multiplied by 100. What did you get? It's a big percent. $1,233.3. We'll go with one decimal, okay, for percentages, percent. Now, let's actually talk about units, because I put them on there as percent, and it would probably be a good idea to recognize why that's the correct unit. 12 and 0.9 are the million users, right? So this numerator is those units right there, million internet users. But that's what the denominator is as well, right? So the units are actually canceling one another out. It's million users divided by millions of users. And so the percent is the only thing that's left. So over this time frame, it has increased 1,200%. Okay, totally possible to increase by a percentage that's very large. That's a doable thing. The last one, average rate of change, takes again the same numerator, so 12 minus 0.9, and it divides by what? This is always change over an interval of time. Yeah. 2000 minus 1997. It's divided by the 3 years. The data is collected over a 3-year time frame. Beginning of the data at the beginning of the 3 years, the end of the 3 years. It's divided by 3 years. So we really have here 11.1 divided by 3. 3.7. What would my units be for this one? Well, what's the units on top? Million users. Million internet users, if you want to be more specific.
Per year?
And then the denominator's years, so it's per year. That's not always per year, because sometimes our data is spread apart in a number of months, or a number of weeks, or a number of days. But, you know, whatever the time frame is, we're looking at the change across.
Are we going to have to list the data range like we did in the models last chapter?
Are we going to have to list the, what'd you say?
The range of X value?
We're about to. Because the directions actually here said to calculate, and then it said to write a sentence to interpret. And we're about to do a sentence.
So just like a model.
Yeah, much like a model. So let's actually take a look to have space. No, of course I don't. Okay, I'm going to have to shrink all this for this to work. Obviously did not plan very well. Okay, you guys have all your numbers written down. At least I hope, because there's no way you're reading that from this far back at this point. I can still see it, but you can't. Okay, here's the deal. We need a sentence that actually hits all of these details. It needs to start with the when. So, Mark, that's the when, like the interval that you were just talking about. When is the interval of time? It's from when to when.
97 to 2000.
Right. So, over here, we're going to start out by saying, from 1997 to 2000. Okay, so we're going to write this 3 times, and every time it's going to say from 1997 to 2000, because it's the same time interval. What is changing?
The millions of internet users.
Yeah, and we don't necessarily need to say millions right now. It's just the internet users, right? Specifically in China in this problem. So the internet users in China. Again, that's the same thing you're going to write for all 3 sentences, because it's the same thing that's changing and over the same interval. 3 says how. Did it increase or did it decrease?
Increased.
It increased, right? It went from 0.9 million up to 12 million. It increased. If it didn't look quite so obvious, you could also look at the values you got and identify. Did it get a positive number or a negative number? Positive numbers means it increased. Negative numbers means it decreased. So the internet users in China increased, past tense, by, and then this is the part that's different. Every single sentence looks exactly the same. So you're going to write this thing down 3 times. Okay? The first time it's going to say with the change. So it increased by 11.1 million users. I already identified they were internet users, so I don't necessarily need to say internet users again. If I did, it would be fine. 11.1 million users. But this piece right here could very easily be replaced with one of the other kinds of changes, right? Sure. So instead of saying that it increased by 11.1 million users, I could say that it increased by, I'll say by again down here, 3.3%. So if I just simply take what's underlined in blue, the 11.1 million users, I rewrite everything else, and I put the words in by 1233.3%. That would be the equivalent for the second piece of information. The third, again, would say by, and I would say by 3.7 million users per year. Three sentences, they're almost identical, right? I know this isn't English, but I'm not asking you to write a whole bunch, just a little bit. 3 sentences. So far, so good? Okay, so Mark, it is a lot like our models, right? We've got a lot of details. The details are always going to have the same sort of structure to them, which makes it easier because it means that I always should have those same details in every single piece. And if I'm missing something, then obviously it's one of these things, right? I'm missing one of those pieces. All right, so we're going to do an example. And we are going to do an example actually from my COVID data. The table below shows the total number of positive COVID-19 cases diagnosed in Oklahoma weekly in weeks after April 1st, 2020. Question A says, what is the change I don't know why it's duplicated there. That's weird. Does yours do that on your paper too? Yeah, it just should say, what is the change? What is the change in the number of cases between weeks 9 and 13? That's what happens when you copy paste. Oh no, yours is fine on paper. Mine is just weird on my screen. Okay, well, week 9 is here, and week 13 is here, right? So it's not given to me in a sentence form like it was about the Chinese users of the internet. Instead, it's given me to it in a table. But what would I do to find the change?
Just the change?
Mm-hmm.
Subtract.
Yeah, I would just subtract the later data, which was the 14,000 number, 14,112, minus my earlier data, which is 6805. So what does that give you? 307? Awesome. What are my units on this? Cases. So what this is actually finding for us is the number of people who tested positive for COVID between week 9 and week 13, right? Specific time frame. Now, notice over here, I'll promise I'll flip back in a second. The directions here told me you have to write a sentence of interpretation, something of that nature, right? So we're not writing a sentence of interpretation every time, kind of like with models, we always write the details, right? We're only doing it when we're asked to. So on this question, we're not asked to write a sentence of interpretation. We're just asked to make a calculation. Calculations still have units on them, so it still needs to say cases. But I don't have to write this out and say, from the 9th week to the 13th week, the number of Oklahomans who contracted had positive. I mean, I don't have to write all that out. It's not what I'm being asked to do on this problem. What I've done so far is sufficient. Sound good?
Yeah.
Okay. B wants to know the same thing, but it wants us to find the percent change and the average rate of change on the same interval. So we're going to calculate two more quantities, percent change and average rate of change. So percent change and average rate of change have the same numerator as what we just calculated. So you can either write down the 7307, or if you want, you can write down 14,112 minus 6805 as your numerator. Same numerator on both parts, 14,112 minus 6805. So on the first one, percent change, what do I divide by? 6805. I divide by the original, over that time frame, the original number of, in this case, cases of COVID. And then I multiply by 100. That is our calculation that we're performing. So what is 7307 divided by 6805 times 100?
107.38.
Okay, we'll do one decimal, Paula.
So 0.4.
Fabulous. 170.4. So over that time frame, it went up 170%.
No, that's wrong. 107.4.
Oh,
I'm sorry.
like this?
107.4, yes.
Okay. I actually had 170 written down, so it's really crazy that I would have written down the same mistake that you had yours. So that's crazy. Yeah, absolutely. Funny stuff. Okay, cool. All right, so 107%. It went up 107%. All right, average rate of change. Numerator's the same. What's my denominator this time? 13 minus 9. It's the number of weeks, the time frame that's passed. Okay, so it's always divided by the time frame that's passed. So again, that's 7307 divided, in this case, by 4. What's that give me? Yep, well, Sorry, percentages we'll use 1 decimal place, everything else we'll use 3, like we have been. Yeah, so you can write 75 or 750 if you want to use the 3 full decimal places.
Are we gonna get 1 second off for homework if we don't have the 0?
Most of the time it'll continue on and you won't even have a choice. Like you'll have to stop it somewhere and you'll stop it at 3. So if you left it off with its 0 trailing at the end, it'd be okay. Oh, it's a good question. What are my units on this?
No.
It's not a percent.
Cases.
Cases, diagnosis.
Cases, what? Close? Per week. The 9 and the 13 were different week numbers. So if you look back at your table, here's my cases, and here's the weeks. So we divided cases by numbers of weeks. All right, grab a calculator because we're going to find a model. We're going to be finding models all semester, but you guys are really good at it now because we spent a whole chapter, whole 4 weeks or whatever we did doing them. So take your calculator, and I want you to put the original data in, and there's no reason to align anything, right? I don't have any years with really big values in my L1 column, so I'm going to enter it exactly like it shows up here. So 7, 8, 9, and so forth. I'm going to show you some cool stuff if we get the document camera to work today as well, so we're going to see about that. We've got it in here. Okay, notice it doesn't tell you what kind of model to create. So you have to look at the data to decide what you want to create. And I believe there's at least a couple options that are reasonable to try. Let's try this.
Exponential.
Exponential is one that would be reasonable to try. What else?
Logarithmic.
So wouldn't it have been nice if it had actually been in here earlier?
Quadratic model that we would only be dealing with progress.
Yeah. So logarithmic models are concave down if they're increasing, so they won't fit this particular description, but you're right about the one concavity part. So exponential and quadratic are possibilities. So we don't know which one's the best, so we're going to try them both. You mentioned exponential first, so we're going to do stat calc. And if we do an exponential regression, you can graph it and see what it looks like. It's pretty good. Agreed? So let's just check and make sure that it's not any better to do quadratic. So I'm going to turn this graph off, and I'm going to do stat calc. We'll do quadratic regression, and I'm going to put it in Y2, so it won't erase my equation, and double check what it looks like with quadratic. I'm really not just like drawn in either direction. They both look really good, okay? So it doesn't matter which one we pick, we just need to pick one if they're both equally good fits. And in terms of end behavior, they both go increasing to infinity, right? I don't have any end behavior to go off of. So I have 2 answers here that are both legit. So just so that we're all doing the same thing, let's pick one. Do you want to do equation that's exponential, or do you want to do quadratic? Exponential, okay. So if you do exponential and you go back to y equals, that equation is in y1. So this is what you're going to have, 1256. All right, so we need a name. This was COVID cases, so I'm going to call mine C of x. You can pick a different name if you'd like. F of x is fine if you want to always use the same. It's 1256.553. And then I have 1.209 to the x.
Cases.
Thank you. Just cases, it's actually cumulative cases, so cases. And then what is x?
Where X is weeks
Since April 1st.
Since April 1st. Yeah,
I didn't print the notes.
that's okay. It's actually since April 1st. So it is weeks since April 1st. And then we have that interval that's 7 less than or equal to x less than or equal to 17. So that's our appropriate model. All right, what I'd like to show you is how to do the next problem, and this is actually why I turned the calculator on with the document camera, is what I can do to show you some really cool tricks that your calculator has. So the first thing I want to do on the next problem is I want to write down what we're going to do. So just set your calculator down for a moment. We'll use the calculator all at the same time so that I can switch between my devices, okay? So this one actually asks us to use the model, not the data. We already did this with the data, but to use the model to find the change, the percent change, and the average rate of change. So over here, when we wrote down all of these sort of calculation formulas, right? We wrote them down with the function f with beta and a, right? We're going to do the same thing here, but we're going to use our function name, which I called mine c, and we're going to use the intervals that we had, which was 9 to 13. So over here, when I'm calculating this, on change, I'm going to be writing down that I've got c of 13 minus c of 9. C because my function name was c, but use whatever you have. And then I had percent change. And percent change says I have the same numerator, c of 13 minus c of 9. And then I divide by c of 9, and I multiply by 100. Again, my calculator is going to be really fun and handy here in a second, and it's going to calculate these for us. And the third one, average rate of change, numerator stays the same, c of 13 minus c of 9. And the cool thing about the way that this actually lines up is that the denominator matches those inputs and just says 13 minus 9. So they look the same, right? You see these pairing up right here? So this is what I want my calculator to do for me, is to make all these calculations. And I mean, you can do a lot of this just, like nitty gritty kind of retyping things in, but I want to show you what your calculator can do so you don't have to, all right? Am I good to switch to the document camera? All right, I told it to. Let's try it again. Okay, so what I'd like you to do is to go into your regular screen, which is second mode. You can clear out what's there if there's anything in there right now. You don't need it. And I want you to pull up that Y1. Hit vars, Y-vars, function, Y1. That's the function that you've stored into Y1 in your calculator. The exponential function we just created a moment ago. And you can actually do a parentheses and 13 and close them. And then you can do the same thing again. Minus vars, Y-vars, function, Y1, and do 9. And your calculator is going to calculate from the equation what is happening in 13 weeks, and from the equation what is happening at 9 weeks, and then it's going to subtract it all when you hit enter. So over onto your actual paper, you can write down 7,925, and you can actually enter it with the decimals, 0.414. The units are still the same. This is still cases, which means we sort of have a problem. Do you see it? I know I don't have my other screen on. Maybe I'll do it real quick so you can see. wrong with writing 7,925.414 cases?
Can't have a decimal number of cases.
You cannot have a decimal number of cases of COVID. Like, it doesn't make sense because these are representing actual people, right? Actual people, actual tests. These are whole number of values. So when I'm reporting this, although the calculator told me 0.414, right? I can't report it that way because it doesn't make logical sense. So we'll take off the 0.414 and it'll be just cases. All right, I don't think I can get it over there. Let's just do it this way. Moving things around and erasing things is kind of funny on this particular program. Okay, any questions on that one? Okay, let's go back to your calculator then. So, in your calculator right now, it already says 795.413906, and it keeps going probably right after that. Numbers of cases. We know that it actually should be rounded to a whole number if we're reporting it. But if we're using it in future information, we don't round, because you wait to round till the very end of a problem so you don't lose any accuracy along the way. So if you will right now just hit the division button, you can tell it, I want to do vars, y vars function y1 of 9, and then times 100, and it will calculate the percent for you. So, you end up with 113. We do have a decimal point on this. It is a percentage. So 113.9%.
Could that be 114?
It would if you were rounding it to a whole number. We're going to use one decimal when it comes to our for our percent values. So we're just always going to use 1%. That's going to be our default. All right. Last one, average rate of change. So you have a couple options. You can type in 7925.413906 and then do divided by 4. It wouldn't be awful. It wouldn't. But I want to show you a cool calculator thing that you can do too. Especially if the decimal expansion maybe continued further, that you wanted to make sure you didn't get any, decimals trailing or losing or something like that. Hit second and entry down here at the bottom, this entry button. And notice it pulled up the previous line of text. But do it again. Second entry. So every time you hit second entry, second enter, it pulls up the previous entry, and you can go back several steps up into your calculator.
Where was this my whole life?
I know. When I first learned it, I know that's what I felt like too. So you can go up a few steps, and the reason that's nice is because that's really like 2 keystrokes instead of me typing out, 10 digits or whatever it was, and I can press enter, and it pulls it right back up. And then I can just hit divided by 4 because I know that 13 minus 9 is 4. If I didn't, I could do it division with that value. And I end up with the average rate of change. And it says 1981.353. What are my units on this one?
Cases per week after cases per week.
Cases per week. Yep. Cases is my numerator. Weeks is my denominator, so this is cases per week. Now, I think I probably should make a comment because it feels a little funny. Because on change, I told you we needed a whole number of cases. But for average rate of change, we can have a partial number of cases. And the reason is because the average rate of change is a rate. It's a rate at which something is happening. Okay, so we don't need a whole number for it to make sense. It makes sense in decimal form because we're talking about a rate, not a number of cases individually. Now, if we had a good model to begin with, the answers from the actual data, what we did on part A and B, and the answers for what we just did on part C using the model, they should be close. If they're not, there's probably either a data entry error or maybe we calculated something with the wrong number in the wrong place, something like that. Or maybe just our model was a really bad model and we forgot to check it and graph it and make sure it really worked. Okay? So if you're comparing these numbers back to A and B on your page, because yours is all on the same page, are they close? They're pretty close, right? A was 79.20, I'm sorry, A was 73.07, and over here it's 79.25. That's a little off. Okay. Oops, and hit the wrong button. On B, we had a percent change. I'm sorry, it was A and D, not C. B, we had percent change of 107%. On D, it's 113, 114%. That's pretty close. And on C, our average caseload was 1826, and on D, it's 1981. Okay, so they're a little off, but they're in the ballpark, right? I'm not off by like huge, massive amounts of numbers. So which answers are more accurate? Those found using the table or those found using the model? And why?
The model,
So why do you think it's the model?
because it uses more of the table we just used 9 to 13, right?
Mm-hmm.
And then on the model, we had all of them to go through.
Okay.
We got more data.
So that's true, but once we used our calculator and calculated it with specifically the 9 and the 13, it sort of would have eliminated that benefit. So that won't be the reason why. Any other thoughts? Nobody knows any reason why one would be better than the other? What is our calculator doing when it finds a model? Martin,
Estimating,
it's what?
estimating.
It is estimating. That's really important. It estimates, right? If you go back and you look at your data, it was close. I mean, like we looked at the dots, we looked at the curve. It was a pretty good fit, and that's really good. But it estimated things, right? It did an approximation. So is the model going to be better, or is the actual data going to be better?
The actual data.
The actual data, because the actual data didn't approximate or estimate anything. Now, I mean, it's only as good as the actual data's values being correct, of course. But it's more accurate with the data than it is with the model because the model approximates. So over here, which answers are more accurate? So the table is more accurate because it's actual data. There are no estimations or approximations. Does that make sense? Sometimes I'll have people tell me that the data from, or that the model actually is better because it gives me more decimal places as well. You know, so like this idea that more decimal places is more accurate. And that could be the case, depending on what you were looking at and what you were estimating, or not estimating, but measuring. But we still have our actual data that's going to be more accurate than an approximate data, which is what the model gives us. All right, let's take a look at some other problems, or one other problem that talks about change, percent change, and average rate of change. The accompanying graph models the number of states associated with the National PTA organization from 1895 through 1931. We've actually had this problem once before. We didn't see a picture for it, though. I don't think we did. I think we looked at a data set instead of a picture. Part A wants us to find the change, percent change, and average rate of change from 1905 to 1915. So part of the reason why I wanted you to see this one compared to the other one is because the data is given to you in a different way. Right? We've had 3 problems today. The first one gave you data in a verbal description. The second one gave you data as a table, and we looked at it from what would happen if we had an equation. So we kind of looked at it from 2 perspectives. And this third one, which is our fourth way, is to take data out of a graph. So it's specifically looking at data in 1905 and 1915. So we need to figure out where is 1905 and where is 1915 on this supporting graph. So 1945 is right here, and 1915 is about right here. Okay, so on your graph, just mark them from where you are up. There's going to be an error in what we do, so mine's not going to be exactly like yours, and that's totally okay. So there's grace given when we're doing approximations, and this is definitely one of those places. So we're going to go from the curve that we've sort of, led up to over to the y-axis and approximate where we are. Mine looks like we're at about 5 for 1905 and about 20 for 1915. Yours may not look quite as close to that on mine because I'm using these really broad, thick pen strokes to try to make it as visible to you as I can. But that's kind of what it looks like. So my data values look like I'm dealing with 1905, and there being 5 states, and 1915, and there being 20 states. Does that seem reasonable? So these are the values that I'm going to use over here as I'm calculating my change, percent change, and average rate of change. So we're going to start with change. What would I be subtracting if I'm subtracting change? Say it loud for me, Jacob.
20 minus 5.
Yep, 20 minus 5, or whatever nearby value it was that you found on your graph. 20 minus 5. 20 minus 5 is 15. 15 what?
15
Yep, that's right. Somebody said it states.
states.
I mean, so we're not writing the sentence again on this one because it didn't tell me I had to, but if I had to write a sentence, it would say something like this. From 1905 to 1915, the number of states with PTA organizations increased by 15 states, right? 15 more states had one of these organizations. Percent change. By the way, those of you who are like, what the heck's a PTA? It probably means that you haven't done public school in America. PTA is Parent Teacher Association. So they have lots of other words for it. Parent Teacher Student PTSA sometimes, or PTO, Parent Teacher Organization. But this is like the coordination between parents and teachers is what it is. All right, percent change is the same numerator, 20 minus 5. What does it divide by? 5. And then times 100. So we have 20 minus 5, which was 15. 15 divided by 5 is actually 3. And then 3 times 100 would be 300%. All right, the last one, average rate of change. Same numerator, 20 minus 5. Your denominator is what?
15 minus 5.
Okay, so either 1915 minus 1905 or 15 minus 5 if you're using just the last 2 digits. Either way, it's 10-year time frame, right? It's a 10-year time span. So we've got 15 over 10, which gives us what? 1.5. 1.5 what? States per, it is per year, right? Because we're dividing by a number of years. This is states per year. Now, it's important to recognize that those years 1915 and 1905 are very specific. So if I change the years, I don't expect to get the same answers. So we're going to do the same calculation again, but we're going to do it from 1920 to 1925. So going back to my picture, I need 1920, which is right here-ish, and 1925 is right here-ish, and we're going to come over here. These are not occurring on very nice values over on my y-axis right now, so I'm going to have to sort of estimate. It looks like it's about 38 and maybe about 43. I don't know, approximately. If yours looks a little bit different than mine, use what you have. That's fine. So my two data values then are not the same as before, of course. I've got 1920 and 38, and I've got 1925 and 43. So we're ready to change, percent change, and average rate of change. All right, so what would I do for change? 43 minus 38, which gives me 5 states. Yep. Percent change is the same expression in the numerator, 43 minus 38. What will I divide by? Somebody said it, 38, and then multiply by 100. So I don't have this one written down. Let me see. Okay, so what'd you guys get? Okay, and if we use just one decimal, it'd be 13.2, right? So 13.2%. And then my last one, same numerator, 43 minus 38. Now I'm dividing by 1925 minus 1920. What do I end up with on this one? It's 1. 1 what? 1 state per year. Now let me just give you 2 thoughts before we stop today. Your answers to part B might look a little bit different. To be honest, the answers in my paper are different. My notes up here are different on B. Because when I estimated from my paper here instead of from the screen, I didn't find 43 and 38. I thought it was closer to 43 and 37 based on the paper that I was looking at, right? So they should be, close. Like if I get 1 state per year and you got 5 states per year, we got a problem. Those are not close. But if I did it with my paper and it says 1.2 states per year and I did it on the screen here and it says 1 state per year, we're in the same neighborhood of values, right? Like it makes sense. So your answer and somebody else's answer might not match up perfectly, especially if you're doing in particular like this from a graph, because you're estimating from a graph. Also notice if you compare these answers on part B to the answers on part A, you might be alarmed and say, well, I don't really understand. I mean, it looks like, my number of states is 15 states on change, and it's 5 states here. So it's like triple the amount, right, of this one. But that's like 300% compared to 13%. Like, what is going on? Well, take a look over here at the table, the graph, and you can kind of see what's going on. There's this really big increase over time in the number of states. Right? It went from 5 to 15. Percentage-wise, that's a really big increase. But the bigger the values are that you're working with, the less the increase looks like each time. So like I could still even increase 15 states in theory, but because I already have, 37 or 38 states, the percentage would not be quite so much. So the reason I mention this is because it's a very interesting thing when you look at the percent changes that's being reported in the newspaper right now for COVID, right? You could actually increase 1,000 cases and the percent's going to be really small. And it might make you feel like, well, that's not very much. And you go back and you look at what happened in April and you're like, whoa, the percents were enormous. Well, of course they were. Not very many people had it. All right, that doesn't make it good or bad, but it makes it something that you should be aware of so that you're not sort of led astray by the values that you're being shown in a particular situation, right? So if you doubled your money and you went from $5 to $10 in your pocket, you're going to be like, yay, doubled my money, right? If you doubled your money and you went from $500 to $1,000 and you have a little bit more excitement. It's that kind of stuff, right? The percentage in that case is the same, but the value is quite different. So something to be aware of. All right, so we are finished with section 2.1. This homework will be due on Monday. We're going to get started on it here in class. Monday's not the right day because you're not with me on Monday. How about Tuesday? It'll be due on Tuesday. Let's go ahead and get out your books or a device if you're using a device that's got your book on there and start taking a look at it before we leave today. We'll go for maybe about 10 minutes or so. That way you can have a chance to try something before you leave. Because I don't want you getting out of here later and going, I thought I knew what she was talking about, and now I don't know what she was talking about. Okay, so give a chance to try a little bit. We'll go for 10 minutes.